Hello learners, welcome to the another week of our course on Introduction to Electric Vehicle and Hybrid Electric Vehicle. In this week, we will discuss about the electric propulsion system or electric drivetrain and its constituent technologies for electric vehicles and hybrid electric vehicles. In past 2 weeks or in past previous lectures, we have seen different vehicle architecture of electrified vehicles such as electric vehicles, hybrid electric vehicles, different configurations of the hybrid electric vehicle like series hybrid electric vehicle, parallel hybrid, series parallel and complex hybrid electric vehicle, along with the plug-in hybrid electric vehicle and fuel cell vehicles. If one closely examines the architecture of these vehicles, then one can easily conclude that there is a good amount of similarity among these vehicles. For example, all these vehicles have battery, electric motor and power electronics converter along with a electronics control unit which is controlling these components. All these components combined together creates a backbone of electrified vehicles, that is electric propulsion system or EV drivetrain. The electric propulsion system functions as the core component of, or as I mentioned earlier, backbone of electric propulsion system or backbone of electric vehicular technology. It replaces traditional internal combustion engine based mechanical propulsion system in vehicles. It offers significant improvement in energy conversion efficiency and vehicle performance. So, an electric propulsion system is playing a crucial role in converting the onboard available electrical energy into mechanical energy to propel or to move the vehicle on road. The fundamental block diagram of electric propulsion system, as you can see, encompasses various elements as mentioned earlier like electronics controller, control hardware, software algorithm, energy systems, power electronics converter, electric motors, etc. The integration of these components define the performance, efficiency and reliability of electric vehicle in today's evolving automotive landscape. So, it is very important to have a proper understanding about electric propulsion system and its constituent technologies and how they are combining and working together. As you can see in the figure, the major component of electric propulsion systems are electronics control unit, energy source and storage system, power electronics converter and electric motor. So, if you examine these components more minutely or in more closer way, then one can see the electronics controller has two aspects, the hardware part and the software part. If you see the hardware part, it contains different kind of microcontroller, microprocessor, digital signal processors, field programmable gate array, etc., or a combination of these microcontrollers and digital signal processors. If you go for the software, it has a different software algorithm to control the driving function of the electric propulsion system, that might include the V by F control, field oriented control, vector control, direct torque control, ANN, fuzzy, etc. Another major component is onboard energy source and storage system. If you talk about the technology, it has battery. Battery can have nickel metal hydride, lithium ion based battery, lead cadmium battery, lead acid batteries. In addition with the battery, the other available sources are ultra capacitors, fuel cells and flywheel. Another important component of electric propulsion system is power electronics converter. If you categorize the power electronics converter in terms of the topology, then the available topologies are DC to AC converter, which is an inverter, AC to DC converter, which is a rectifier, and DC to DC converter. These are the three major power electronics converters which are used for vehicular electrification or which are used in electric propulsion system. If you talk about, if one can talk about the devices that is being used in these converters, then they are the IGBTs, MOSFETs and in future one might get the silicon carbide and gallium nitride devices for the synthesis of these power electronics topologies. In addition to the topologies and devices, the another important part for power electronics converter is the control mechanism, the pulse width modulation techniques, and the family of pulse width modulation techniques are widely being used to control these devices and consequently to control the operations of the power electronics converter topologies. The another most important component is the electric motor. The available options for the electric motors are the induction motor, permanent magnet synchronous motor, switched reluctance motor, and DC motors, and there are different design methods and tools are available for designing these motors, such as finite element method, etc. So, the effective integration of these components is crucial for electric propulsion system to compete with traditional internal combustion engine based mechanical propulsion system. To realize the vision of sustainable electric vehicle, electric propulsion system must address several key factors which are very important while designing the electric propulsion systems. Some of these key factors are driving profile, vehicle weight and volume, reliability and flexibility, compact packaging, cooling mechanism, and maintenance. These all factor needs to be taken care with affordable cost. If we look into the current status and the future trends of this electric propulsion system in terms of their R&D status and the target in past a decade from 2010 to 2010-20, then one can see the reduction of the cost in per kilowatt. In 2010 it was somewhere around greater than $19, and now by 2020 it is less than $8, and it might be possible we have a significant reduction by 2030. Another thing one can notice is the power density. It has to increase over a period of time. So, in 2010 the power density was somewhere 1.6, and now we are having power density more than 1.4 per kilowatt per liter. Similarly, if one talk about the specific power in terms of the kilowatt per kg, then in 2010 it was greater than 2.6, in 2015 it is greater than 3.5, and by 2020 it is greater than 4, and might be by 2030 it would be somewhere around greater than 5 or 6. If we talk about the efficiency, the efficiency of electric propulsion system in 2010 it was somewhere around 90%, in 2015 it was 93%, and by in 2020 it was 95% approximately. This is the tentative figure. As the R&D will progress, as the technology will grow further, the significant improvement in efficiency, in specific power and power density will be seen, however, with the reduction of cost in coming days. So, developing sustainable electric vehicle with advanced electric propulsion system demands targeted planning and collaborative effort to achieve enhanced performance and efficiency and reliability while reducing the cost, weight and volume. Such advanced electric propulsion system will certainly bridge the gap between the electric propulsion system research, development and its successful commercialization. So, let us have a small comparison between the electric propulsion system and mechanical propulsion system to have a better appreciation about the role, responsibility, to have a better appreciation about the roles and responsibility of electric propulsion system that it is taking care as far as the development of electric vehicle is concerned. So, if we compare the EPS and MPS both in terms of the energy source and efficiency, then EPS utilizes electrical energy stored in batteries, fuel cells, ultra capacitor, etc. to drive an electric motor. Electric motor are highly efficient, converting over 80 to 90% of electrical energy into mechanical energy. This efficiency is significantly higher than that of mechanical propulsion system. leading to lower consumption and operational cost. If you talk about the mechanical propulsion system, it typically relies on the combustion of the fossil fuels to power the internal combustion engine. The efficiency of mechanical propulsion system is much lower and generally around 20 to 30%. Hence, significant portion of the energy is lost as heat during the combustion. If you compare the EPS and MPS in terms of the component and complexities, then EPS comprises an electric motor, battery pack, power converter as discussed earlier. It has fewer moving parts, leading to simpler design, reduced mechanical wears and lower maintenance requirement. Whereas in mechanical propulsion system, it includes a combustion engine, transmission, fuel system, exhaust system and various mechanical linkages, as we have discussed in the beginning classes, where we have discussed the architecture of the internal combustion engine. So, all these components have been discussed and mentioned with the great detail. So, these components are more complex with numerous moving parts that requires regular maintenance and are prone to mechanical failure. The electric propulsion system leads to zero tailpipe emission or very less tailpipe emission in case of hybrid electric vehicle, contributing to significant reduction in greenhouse gases and air pollutants. The environmental benefit depends on the source of the electricity used for charging. If we integrate the renewable energy sources, the further benefit can be achieved. Whereas in mechanical propulsion system leads to emission of CO2 and NOx gases and other harmful pollutant during combustion, contributing to air pollution and climate change. The reliance on the fossil fuel also lead to the our dependency on the depleting fossil fuels and all. Mechanical propulsion system leads to emission of CO2 and NOx gases and other harmful pollutants during combustion, contributing to air pollution and climate change. If we talk about the performance, the electric propulsion system provides instant torque resulting in rapid acceleration, smooth operation, the power delivery is linear and regenerative braking system can recover energy during deceleration and improves overall efficiency. Whereas in mechanical propulsion system, performance is influenced by the engine characteristics and the capacity with lag in power delivery due to the combustion process, and energy recovery is limited as compared to electric propulsion system. As far as the noise and vibration is concerned, the electric propulsion system operates almost silently with minimal vibrations, leading to quieter and more comfortable driving experience. However, the mechanical propulsion system generates significant noise and vibration due to the combustion process and moving parts, contributing to a noisier and less refined driving experience. One can easily feel the amount of noise and the vibration with conventional mechanical propulsion system based vehicles. If you compare both the propulsion system in terms of the cost and infrastructure, then the electric propulsion system's initial cost is high, however infrastructure is limited, whereas in mechanical propulsion system the initial cost is low and it has well established infrastructure. So, this is a brief comparison about the electric propulsion system and mechanical propulsion system, and this table gives a quick summary of the comparison between the electric propulsion system and mechanical propulsion system. So, in summary, the electric propulsion system offers superior efficiency, environmental benefits and lower maintenance requirement compared to traditional mechanical propulsion system. However, the choice between these two propulsion system still depends on the factor like availability of infrastructure, initial cost, specific use and applications. Now, let us discuss the different constituent of electric propulsion system to enhance our appreciation for this component. So, the first component that we will discuss is the onboard energy source and storage system. The strength of the electrical energy source and the storage system plays important role in vehicular electrification. Basically, the energy source and storage system includes the source like fuel cell and onboard storage devices like battery, ultracapacitor and flywheel. Battery and fuel cell produce onboard electrical energy by means of electrochemical energy conversion. However, the battery stores energy whereas fuel cell generates energy. The detailed discussion on the fuel cell and battery will be available in coming weeks. Ultracapacitor on the other hand relies on electrostatic principle to store the energy and act as a source of high power density, whereas flywheel stores energy in mechanical form. The efficiency, fuel economy and all electric range of electric vehicle are highly dependent on onboard energy source and storage system. The onboard energy source and storage system must be sized such that they store sufficient energy and provide adequate peak power to meet all driving profile. In another terms, the onboard energy source and storage system should have a good energy density and power density. The main factor that affects the design of this onboard energy source and storage system for vehicular application includes the energy density, which defines the driving range, the power density, which defines the top speed that a vehicle can deliver or an electric propulsion system can produce, the life cycle of the storage system, the size, safety, maintenance and along with the durability and reliability. Furthermore, the recyclability is also one of the important factor. So, these all factor needs to be taken care and that too at reasonable cost while designing the onboard energy source and storage system for electric propulsion system or for electric vehicle. The basic characteristics of different energy source or the basic characteristics of the specific power versus specific energy of different energy source that I have mentioned such as fuel cell, battery, ultracapacitor, flywheel along with the gasoline based IC engine is shown in this figure. One can easily see that ultracapacitor has a very high specific power or it has a very high power density, whereas the fuel cell has a very high specific energy or very high energy density. So, and if you can see the gasoline based IC engine offers a decent specific power as well as specific energy. It can be observed from this figure that each of these energy source has specific characteristics and their dominance comes accordingly. Suitable integration of these sources to form hybrid energy system is an interesting and challenging field for both researcher and manufacturer. So, let us discuss the different part of this energy source and storage system. So, the first part or the first item of onboard energy source and storage system is the battery. As we all know, a battery converts chemical energy into electrical energy during discharging and electrical energy back into chemical energy during charging. The electrochemical battery consists of a multiple cell, each possessing electrochemical properties capable of storing or delivering energy either individually or collectively. Depending on their configuration, they deliver particular amount of power and energy. The key factors driving battery technology in vehicular electrification includes high energy density, its modularity, flexibility and affordability at certain model or up to certain degree. In electric vehicle technology, the battery serves as the primary onboard energy storage, offering high energy and power density to support complete driving cycle. The required battery characteristics vary across different vehicle types, like electric vehicle need high energy density batteries, hybrid electric vehicle and fuel cell vehicle requires high power density batteries, while plug-in hybrid electric vehicle demands a balance between energy and power density. Lithium based batteries such as lithium ion and lithium polymer as well as nickel based and lead acid batteries are suitable for EV applications, or these are some of the battery type which are being used for used in electric propulsion system for vehicular application. Among these, lead acid batteries are used for short term application due to their low energy density, while lithium and nickel based batteries are favored for medium and long term use. Though the nickel cadmium and nickel metal hydride based batteries are mature with limited potential for further improvement or cost reduction, the lithium based battery continue to attract attention in future due to its high energy density, low weight and cost effectiveness. Moreover, the potential of lithium based battery is still being explored and their maturity level has yet been fully achieved. As a result, lithium based batteries and solid state batteries are regarded as the future of battery technology for powering electric vehicle. The dominant characteristics and comparison of various battery technologies are presented here in terms of the nominal cell voltage, specific energy, energy density, specific power, power density, self discharging percentage, life cycle and operating temperature. So, based on these characteristics and features, one can choose the particular battery for a particular electric propulsion system. So, if there is a competition for selection of a battery, whether one should go for a lithium based battery or a nickel based battery or lead acid battery. So, this particular table along with these characteristics will certainly help in identification of the battery for a particular application, or one can assess one's battery requirement based on these characteristics, and accordingly one can choose whether the lithium ion based batteries are good, or whether lithium polymer batteries are good, or whether nickel metal hydride based batteries are good, or whether nickel cadmium based batteries are good. So, any selection of the battery has to go through this particular comparison of the battery, and accordingly one can select and identify the battery technology. Another component is the ultra capacitor. Ultra capacitor is an electrochemical device which works on electrostatic principle to store energy. Therefore, it can be charged, discharged hundreds and thousands of times without degrading the performance. Basically, in ultra capacitor, porous carbon electrodes which offers high surface area are impregnated with electrolyte and small charge separation created by the dielectric separator between this electrode. So, appropriate modification in material selection and fabrication brought the ultra capacitor far away from conventional capacity with very high capacity. The capacity can reach to hundreds and thousands of farad, which directly defines the energy storage ability. So, the ultra capacitor stores energy higher than the traditional capacitor, but lower than the battery, and hence it can be used for application reserved for the battery and capacitor. Ultra capacitor offers higher power density, long cycle life and efficient operation, since the rate of charge and discharge are determined by its physical property. Hence, ultra capacitor can release energy much faster with more power than a battery that relies on slow chemical reactions. Ultra capacitor have been used for IC engine based vehicle like tanks and submarine for starting due to its ability to deliver burst power. So, the ultra capacitor is being used to ignite the fighter tanks and the submarines in the IC engine based vehicles. So, in electric vehicular technology, ultra capacitor can be used as a primary energy device for power delivery during starting, acceleration and hill climbing, as well as for recovery of braking energy during regenerative braking. The combination of ultra capacitor with the battery improves the energy performance of the former with greater energy storage capability of the later. It can be downsize as well as extend the life of battery, reduces maintenance and replacement cost. In future, it is expected that the ultra capacitor can become a major dominating technology in vehicular electrification. However, the desired energy density at reasonable weight and cost is a major concern. The another component of the onboard energy source and storage system is the flywheel. Flywheel, which stores and delivers mechanical energy through rotational kinetic energy, have been studied for decades. However, their adoption in vehicular system has been limited due to their heavy weight and high cost. Recent advancement in frictionless magnetic bearing, carbon fiber composite manufacturing techniques and sophisticated power electronics converter have revitalized the development of flywheel energy storage system. These advancements have enhanced the power density, reliability, efficiency, operational speed of the flywheel while reducing the size and weight, making them promising candidate for energy storage in electric propulsion system. In a flywheel, energy storage is proportional to its mass and square of its velocity. The flywheel accumulates mechanical energy by accelerating and discharging it by decelerating, delivering energy as needed through an integrated motor, generator and power electronics converters. Another important part or a member of onboard energy source and storage system is a fuel cell. Fuel cell is a technology that converts hydrogen into electricity. Recent advancement in fuel cell technology have paved the way for its integration as onboard energy source in electric propulsion system and electric vehicles. Fuel cell offer numerous advantages including eco-friendliness, operational simplicity, continuous power supply, durability, quiet operation while adhering to stringent emission standards. They effectively combine the benefit of internal combustion engine, which provides continuous operation as long as fuel is supplied, and batteries which generate electricity directly from fuel without combustion. Consequently, it reduces the emission and generates less noise and increases the efficiency. A fuel cell is an electrochemical device that generates electricity by combining hydrogen with oxygen from the air, producing water and heat as byproduct. A catalyst such as platinum accelerates this reaction. This direct conversion of hydrogen energy into electrical power bypass the intermediate step of heat conversion, enhancing overall efficiency. While fuel cells have a specific energy comparable to gasoline, their specific power is lower, leading to poor starting performance in fuel cell vehicle. To address this, battery or ultra capacitor are often used in tandem with the fuel cell to improve power density and starting performance. Thus, a fuel cell and ultra capacitor complement each other, providing an optimal energy storage and supply solution for automotive applications. So, in this table, a different onboard energy source and storage system has been compared in terms of the mechanism, technology, energy density, power density, charging time, discharging time, lifespan, efficiency and issues. So, the designer need to go through this particular table to pick a particular energy source for electric propulsion system or a combination of this energy source, making a hybrid energy source for the electric propulsion system. Now, the another important member of electric propulsion system is electric motor. In electric propulsion system, electric motor are subjected to frequent starts and stops, rapid acceleration and deceleration, as well as varying conditions such as low speed hill climbing, high speed cruising. These conditions differ significantly from the stable operating condition of industrial motor, which typically run at a constant rated speed under uniform circumstances. Consequently, the electric motor used in electric propulsion system must meet specific performance criteria that are essentially required for vehicular applications. So, electric motor used in electric propulsion system must exhibit several key characteristics such as high torque for effective starting and hill climbing at low speeds, high power density to support acceleration and high speed cruising on highway, high efficiency across a broad range of torque and speed, suitability for regenerative braking, overload capability for short periods, and overall controllability, reliability and robustness, all at reasonable cost. Additionally, the design considerations should also include fault tolerance, minimal torque ripple, effective temperature management and low acoustic noise. The suitability of an electric motor for propulsion application is often assessed based on its torque speed characteristics. The figure A shows the ideal torque speed characteristics which is required for propulsion application, and B shows the torque speed characteristics of electric motor. As I mentioned these characteristics earlier for different requirement of the vehicle, one can easily appreciate and come to the conclusion that the torque speed characteristics of an electric motor is very much matching and similar to the torque speed characteristics of electric vehicle. So, this is the classification of electric motor. Electric motor can be categorized into two categories: commutatorless and with commutator. With commutator is the family of DC motor, and commutatorless motors are induction motor, permanent magnet synchronous motor and switched reluctance motor. The selection of electric motor is critical aspect of overall performance of electric propulsion system. Current research and industry practice suggest that the squirrel cage induction motor and permanent magnet motors are highly suitable options for APS, whereas the switched reluctance motor are gaining traction as a reliable alternative for future use, while the popularity of DC motor is gradually diminishing. So, let us discuss this motor one by one to appreciate their application in electric propulsion system. So, traditionally DC motor have been used for electric propulsion system due to its high starting torque and simple speed control. The torque speed characteristics of DC motor exhibits good compliance for propulsion application. However, the inherent disadvantage of bulky construction, low efficiency and the presence of mechanical commutators and brushes that aggravate maintenance requirement limits its use in maintenance free vehicle application. Another motor technology is the induction motor. Induction motor based propulsion system are well established and widely accepted as leading candidate for electric propulsion system among commutatorless motors. Induction motor offers numerous advantages including its simplicity, high reliability, robustness, wide speed range, low maintenance, minimal torque ripple, noise, less noise, cost effectiveness along with the established power electronics converters. They also perform well in a very hostile and harsh environment. By employing the advanced control algorithm like vector control, DTC or field oriented control, induction motor can deliver performance characteristics very much similar to those which is delivered by a DC motor. However, induction motor also have some drawbacks such as higher losses, poor power factor, lower efficiency and increased inverter usage as compared to permanent magnet motor. Another motor type is the permanent magnet motor or permanent magnet synchronous motor. Among commutatorless motor, PMSM motor stand out as a strong competitor to induction motor in electric propulsion system. Recently, permanent magnet motor have gained widespread acceptance among leading vehicular manufacturer for both current and future electric vehicle design. Permanent magnet motor are typically classified as brushless or brushless BLDC and brushless AC. To optimize torque density while minimizing torque pulsation, permanent magnet motor are ideally operated in brushless DC mode for trapezoidal back EMF waveform and BLAC mode for sinusoidal back EMF waveform. This permanent magnet motor offers several inherent advantages. They use permanent magnet to excite the field, resulting in high power density, reduced weight and smaller volume for given power rating. Reduced rotor losses contribute to high efficient operation. Compact design ensures higher reliability and maintenance free operation, and effective heat dissipation enhances overall thermal management of the motor, or one can say overall cooling efficiency of the motor. However, permanent magnet motor do have limitations, including a short constant power region due to limited field weakening capability. Additionally, managing back EMF at high speed requires larger power electronics converter and possesses and hence gives challenges in fault tolerance application. The last motor category in this is the switched reluctance motor. It is increasingly being recognized for their potential in electric propulsion system for vehicular application, particularly in hybrid electric vehicle and fuel cell vehicle. The SRM motor offers several notable advantages. They feature a rotor without magnet and windings, leading to a simple and robust construction, ideal for high speed and high temperature operation. Their excellent torque speed characteristics, fault tolerance and the ability to extend the constant power region enhances the performance of switched reluctance motor. However, switched reluctance motor also have some drawbacks, including high acoustic noise, vibration, torque ripple, complex control mechanism and need for specialized converter topologies. Despite their relative high cost, mass production is anticipated to make switched reluctance motor more cost effective comparable to induction motor or other motor technology available for electric propulsion system or electric vehicles. So, while the benefit of switched reluctance motor make them suitable for vehicular application, addressing their limitation is crucial for developing a sustainable solution for electric propulsion system. These motors can also be compared based on controllability, size and weight, robustness, reliability, power density, efficiency, speed range, lifetime, torque density, technical maturity, cost and overload capability. So, each of these characteristics can be given 1 star to 5 star. 5 star means the best suited machine for a particular characteristics and 1 star means worst suited or least suited a machine against the particular characteristics. So, this particular comparison can help the designer to identify the particular motor technology for their application. This comparison is derived based on the available literature and hence it is treated as tentative or approximated one. However, the actual comparison might vary based on the design considerations and the particular specific design considerations and the application for which it has been manufactured. So, this is all about the electric motor. So, in this lecture we have seen the electric propulsion system and its constituent technology for EV and hybrid electric vehicle application. We have discussed the onboard energy source and storage system and available electric motor solutions for electric vehicle. I hope the learners have received the good insight on electric propulsion system and energy source and electric motor. Thank you so much.